Hi, welcome to ISE503. This lecture is Relational Databases Part 2, and the lecture slides are taken from our textbook, which is Principles of Database Management. So in this lecture, I will discuss about normalization, which is a very important concept in relational database management system. So in normalization, these are the topics that we will discuss. I'll start with the insertion, deletion, and update anomalies. We'll see what these things are and how these are related with normalization. Then before we start the formal discussion of normalization, we'll have a look at the informal normalization guidelines. There we will see how an unnormalized relation would look like and how informally we could refine those unnormalized relations into normalized relations. After that, I'll discuss about the functional dependencies, which is a very important concept in understanding normalization. After introducing functional dependencies, you look at the definition of prime attribute type. And then, after understanding functional dependencies and the concept of prime attribute types, then we will discuss normal forms in more formal way. So let's get started. And here you are looking at two relations. The first relation is supplies, and then the second relation is purchase order line. So if we go over the supplies table or the relation and try to understand the columns here or the attribute types, then for supplies in this relation we have supplier number, product number, purchase price, delivery period, supplier name, supplier address, then there are a few more attribute types followed by a product name, product type, and again few more attribute types. Now we need to understand this relation supplies. In this relation, we have the information about supplier as well as the information about product. So the first attribute type that you're looking at is supplier number or SUPNR. And the second attribute type here is PROD NR, which is product number. So we need to understand the assumption behind this relation. In this relation, we have the information about the supplier and the product. And here, a supplier may supply multiple products, and a product may be coming from multiple suppliers. Therefore, if you understand this assumption, then just supplier number or just the product number is not going to be enough for our primary key. Therefore, our primary key is going to be this composite attribute type or this composite, because for primary key we would need supplier number as well as the product number. Okay, so fine, we will go to these technicalities of the primary key and all. But even before that, if you just eyeball over this relation, you would realize that we have some redundancies. Look over here. Daily Wines, that's the supplier name. Daily Wines again. And then we have supplier address. Supplier address is appearing again. The product name, well, the product name is appearing again. So the reason why I thought, okay, fine, we will have the discussion about the composite primary key. But before that, let's look at the relation and try to see if we have the redundancies or not. Then yeah, you can see we have a lot of redundancy or the duplication, which is a bad sign. So the redundancy in your database would result in a lot of problems, right? Like the insertion anomaly, deletion anomaly, and update anomalies, right? So these are a few things we will discuss. So back to what I was discussing before, giving you this idea about redundancies or the anomalies. Redundancies, sorry. Let's see what is our primary key. Our primary key is supplier number and product number. We need all these. We need these two attribute types together to uniquely identify a tuple in this relation. Now let's think about a supplier who is just coming into business, right? So we have supplier but the supplier has not supplied any product yet. Therefore, we will have the supplier number, but we won't have any product number because the supplier is new and the supplier did not supply any product. So the entry of the supplier is not possible in this relation, because if we want to keep a supplier with no product supplied yet, then for product number we'll have to put the value as null. Okay, and null value is not allowed for an attribute which is an attribute type which is a part of primary key. This is called insertion anomaly, which means that you cannot insert um, the information about supplier here in the scenario if the supplier has not supplied any product. Okay, and similarly you can not have the information about a product in this relation if the product does not have any supplier, right? So that is an example of insertion anomaly. I would request you to pay attention to what I'm explaining, because probably in my lecture notes I don't have this thing provided in words, right? So you will have to take this definition from what I'm explaining. Okay, so one more time, insertion anomaly means that in this kind of relation like supplies, you cannot have just a supplier information that does not supply any product, because the primary key is composite with the supplier number attribute type as well as the product number attribute type. Similarly, you cannot have a product number or a product data without a supplier. The same thing, in that case you'll have to put supplier number as null. That's the example of insertion anomaly. Now what is deletion anomaly? Deletion anomaly is kind of similar to insertion anomaly, but it is in other direction. So for that, let's think about a supplier, right? And a supplier is supplying only one product. Okay, or let's think about a product which is supplied by only one supplier. So if the supplier goes out of business, then you'll have to remove the product as well, because you cannot have the product information without a supplier, right? And vice versa. So that is called the deletion anomaly. In update anomaly means that whenever we have to modify one record, as an example, let's think about supplier number 21. For supplier number 21, if you change the address of the supplier, right? So supplier is Daily Wines. If the Daily Wines relocates to a different location, then that update you'll have to do in multiple records, which will be inefficient, right? So what we did before we started the discussion of the normalization and all, we started with a motivation. And in the motivation, using a simple example of supplies here, we kind of understood these three anomalies: insertion, deletion, and update anomalies. This is an extremely important topic because we need to understand normalization. But before normalization, we should know what would be a problem if a relation is not normalized, if the relation has some redundancies or duplicate information. So fine, this is what we had, but probably it doesn't look good. What we should do, we should have better organization of our database. So this whole data that you're looking at is for the purchase order administration. Now, few things that we can easily see over here is that we are, unnecessarily combining the information from two entity types like supplier, because these attributes like supplier number, supplier name, supplier address, that is, these are the attribute types of supplier entity. Whereas the product information that you have like product number, let me write product here. The product number is an attribute type of product entity. Similarly, you will have product name, product type, and then we should have put these, uh, delivery period, purchase price in a different relation. So this looks problematic. What we need is something like this. Okay, so and this is what we will learn to do. Normalization is about these things only. You'll be given a relation like this. These two relations, they are not normalized. They are unnormalized, so they have these anomalies. What we would learn to do, we would learn to make them more efficient, make them normalized, and normalized relations look like this. Okay, we would have the supplier information in supplier relation, we'll have the product information in product relation, and then we will have a supplies, another relation that will have the information about the relationship type between supplier and product. Okay, and then you would have the purchase order relation and purchase order line. So this is where we have to go. This is the final end result that which we'll have once we understand the importance of normalization. Okay, and now question arises, like, what did we gain by normalization? So that's what we would learn. Okay, so to have a good relational data model, all relations in the model should be normalized, right? So that's our motivation. Now, well, a formal normalization procedure can be applied to transform an unnormalized relation model into a normalized form. So, you may understand, you might have, followed what I discussed till now, like the problems associated with unnormalized relations rather, not forms, my bad. So the problems associated with unnormalized relations, okay, like these three anomalies, what we want to normalize them. And I did show you how the normal, relations should look like. But the question is, how do we normalize an unnormalized relation? Okay, so for that we have formal normalization procedures that should be applied to transform an unnormalized relation model into a normalized form. Now, okay, we will learn about all these things, but what is the advantage? Why should we spend time in normalizing the relations, right? So there are two advantages. Advantages are twofold. Let's look at those. Now, at the logical level, the user can easily understand the meaning of data and formulate correct queries, right? So let me take you back to this relational data model. Alright, so here, if you have to write a query, if you have to retrieve data, right? Let's not get into query now right now because we still need to learn about SQL. But yeah, once you know that this is how your data is modeled, right? In supplier relation, then product relation, supplies relation, purchase order relation, and PO line, right? So then it is a lot convenient for you to understand at the logical level, like, yeah, which data goes in which relation, right? So forming the formulation of the query is going to be a lot easier. So that's the first advantage. At the logical level, the user can easily understand, this is important, the meaning of data and can formulate correct queries. The other advantage is, which is at the implementation level. At the implementation level, the storage space is used efficiently and the risk of inconsistent update is reduced. Right? You won't have the duplications, you won't have redundancies. So by getting rid of redundancies, again you are having two advantages in at the implementation level as well. First, you're getting rid of the wastage in storage space, right? You don't have redundancies there. And yeah, the other advantage of reducing the redundancy would be that inconsistencies would be reduced. You'd save the storage space, and yeah, it will be more efficient and inconsistencies won't be there. Okay, good. So let's continue this discussion and let's see what is the information normalization guidelines. Here again, it will not be very technical stuff till these one or two slides, and after that, yeah, we'll get into little detail and we'll learn few interesting stuff. So informal guidelines that we have for normalization goes like this. Design a relational model in such a way that it is easy to explain its meaning. The very basic thing about programming, I would say, right? It goes over here, like how the identifiers should be named. So these things that I'm adding up here is related with any programming thing, right? Like the variables that you have in your program, that they should be descriptive, meaningful. So the same kind of thing applies here also. So let's look at this very first example that we have. So if for some reason you have named your relation like this, you're saying my relation 123. Okay, so giving a relation name like my relation 123 is probably not a good idea, because by this name of the relation you are not conveying any information about relation. Okay, in your relation, yeah, you do have these attribute types like sup and r, which is supplier number, sup name, supplier name, sup twitter, right? Maybe the tweets that the supplier has done, written. Then you have PROD, product number, product name, and so on. So one good thing that we have about this relation, which is my relation 123, is that you have meaningful attribute type names, but for some reason the relation name is not meaningful, is not conveying any information. Therefore, we should rather give a meaningful relation name as well. We should say supplier. Why? Because this relation is about supplier, and in this relation we will be keeping the information related with the supplier, right? So yes, supplier. If your relation is about supplier data, call it supplier. If your relation has the data about student, call it student. Okay, so yeah, very simple thing, but yeah, very important at the same time. Now, the other thing that we have, as the guideline says, that the attribute types from multiple entity types should not be combined in a single relation. Okay, so if you remember the very first example that I had in this lecture, where we had the relation that had the attributes from supplier and also the attributes from the product. So yeah, that thing should not be done. So the second guideline here is highlighting that aspect of the normalization, which says that attribute types from multiple entity types should not be combined in a single relation. So I don't want to show you what I have in the next bullet. Anyway, I'll take you there. But before that, I want to discuss another very interesting thing, which relates with the second bullet. Now, if you look at the supplier, right? So the supplier relation has the attribute type, which is supplier number, SUPNR, supplier name, subname, supplier Twitter, and product number and product name. So what we should do, this supplier should be broken into two relations. One relation which will have the information about supplier only, and the second relation would have the information about the product. So we'll call one relation as supplier relation, the other relation we'll call as the product relation. Okay, and then even in the supplier relation, if you look at these attributes, so let me do it here, right? Just to I'll have to do some writing. Supplier, CPPLIER. Now we'll have supplier relation, and the supplier relation we are going to put these attribute types, sub and R, right? That will be our primary key. Then you will have supplier name, supplier address and all. I'm not going to write those things. I'll write supplier Twitter, and let me put some bullets here, just for those missing attribute types that I did not list here. Now guys, even for this relation, right, there is an issue. The issue is that for suppliers that we are having, probably all the suppliers may not be using Twitter. Okay, so let's assume that in the supplier table, for some reason we have more than 50% people without Twitter account. If that's the case, then expect null values here, right? Which is, kind of giving us a signal that we should better organize this relation also by breaking it down into further two relations. One relation with the supplier and the supplier's Twitter information only, and the other relation should have the supplier with the attributes types where we have the data for almost all the suppliers. Okay, so now let's discuss that the same concept in the next bullet. Avoid excessive amount of null values in a relation. Okay, and for that we have the same example of supplier. You would like to split the supplier table or supplier relation into two relations, like supplier one with the normal supplier attribute types like supplier number, supplier name, supplier address, supplier status. Okay, and then the other relation would be a supplier Twitter, because you here in this relation you're keeping the the tweets related with supplier, right? So supplier number and supplier Twitter, right? More efficient, much better. So guys, make sure that you understand what I'm explaining over here. This is probably one of the most important topic in relational DBMS, RDBMS. Okay, fine. Now let's get to the more technical details. Functional dependencies. Again, a very important concept. Functional dependencies. It's kind of mathematical. That's the reason I love this concept a lot. Okay, so once we understand what is functional dependency, then we'll try to understand the concept behind prime attributes. So here we go. A functional dependency, which is usually represented as x to y, and we use this arrow symbol, right? X functionally determines y. That's how we write it. So the arrow symbol shows the direction, like which attribute. So here y is functionally dependent on x. Okay, and there is a functional dependency between x and y where x functionally determines y, right? So these things we'll discuss. So a functional dependency x to y between two sets of attribute types x and y implies that the value of x uniquely determines the value of y. Okay, so you'll be given a relation R, right? And in this relation R, you'll have a lot of attribute types. Okay, so let's say you have x1, then you have x2, so on and so forth, xn. These are n attribute types for a relation R. Now from these n attribute types of the relation R, you can pick a subset, you call that x, and another subset, you call that y. Okay, and then once we have these subsets x and y from R, now we can evaluate whether we have a functional dependency between x and y or not, or whether the subset of attribute types that I have in X functionally determines the attribute types that I have in the set Y. All right, so let me read this thing one more time, guys. Again, extremely important topic. Make sure that you understand the definition, and make sure that you can work on problems related on this functional dependency concept. So functional dependency x to y, which is x arrow y, between two sets of attribute types x and y, implies that a value of x uniquely determines the value of y. Now, if there is a functional dependency from x to y, okay, so how we can rewrite it, right? So there are multiple ways of stating the same information. We can say that there is a functional dependency from x to y, or we can say that y is functionally dependent on x, right? So from either you describe that from the point of view of x or from the point of view of y. So x functionally determines y, or y is functionally dependent on x, right? It's the same thing. Let's look at some example. If you have a relation which is about an employee, right, then in that employee relation you should expect some attribute types like social security number, SSN. So if you know the SSN of an employee, then using SSN you can determine the name, because the SSN of an employee is supposed to be unique. It's a unique value, right? So if SSN is given to you, you will determine the person. right? So we have the functional dependency starting from SSN to employee name, right? But it is possible that in your organization you may have more than one employee with the same name, e-name, right? Therefore, if you are thinking about the other way of functional dependency, like give me the employee name, I'll tell you the social security number, then yeah, that does not apply. Okay, so employee name does not determine the social security number, because it is possible that we may have multiple employees with the same employee name. Okay, so we should be careful about this functional dependency. We will use it only when X that we have here. So let me put X. X is social security number. X functionally determines, right? Yeah. Y is functionally dependent on X only when, given the value of X, you can uniquely determine the value of Y. So let's look at one more example of functional dependency. If you're working on a project, right? So we need to understand the background. If we have project information, then let's go the assumption that we have in a company setup where we have employees and projects. The scenario is that an employee may work on multiple projects. This is common. And at the same time, one project may have multiple employees. Now, if an employee is working on multiple projects and a project has multiple employee, then we need to keep account of the hours that an employee is putting in a project. All right. So, okay, I think I should use this explanation later. That doesn't apply to this example. So sorry about that. I'll discuss that example later. Let me confine to this one. Here, we have in fact two functional dependencies written in one statement. It is very common to write this way. Our X here is P number, which is project number. So if the project number is given to you, you can uniquely determine the project name. Okay, because yeah, the project number should be unique. It's the primary key. Okay, so given the project number, you will know the project name. Similarly, given the project number, let me write that X is your project number, right? P number. If you give me the project number, I'll tell you the project location. Right, so here again we have the functional dependency. Project number will uniquely determine project name, as well as it will uniquely determine project location, right? So what we do at times, we combine these to the right hand side into one statement, but yeah, you can break it down to two statements as well, or rather two functional dependencies. That's what I'm saying. Let me mark it with numbers, number one and number two. So what I'm trying to explain is that the functional dependency that you have in number two can be broken down into two. One functional dependency, which is P number to P location, and the second one would be P number to P name. Okay, good. Yeah, wait a second. I have introduced a lot of clutter. I will erase this thing, right? And now goes the example for which I was explaining, right? So let me explain that thing one more time. My previous explanation was not correctly timed. I apologize for that. But here, let me repeat the explanation that I had earlier given for the second example. Here we have the third example of functional dependency. So that's about the case where we have multiple employees working in one project, and for one employee can have multiple projects, right? So one employee may be working on multiple project, and for one project we may have multiple employees. So in that kind of scenario, when we want to keep trace of the number of hours an employee is working on a project, then for that we would need the social security number of the employee as well as the project number, right? So in this case, interestingly, this general X to Y functional dependency case, our X has two attributes, social security number as well as the project number. Okay, so the combination of social security number as well as the project number is required to uniquely find out the hours. All right, so I hope you got it. Okay, so let's keep moving. The functional dependencies and attribute types, what we have here. Now we have the definition of the prime attribute. What is prime attribute? A prime attribute type is an attribute type that is a part of a candidate key. I hope you remember what a candidate key is, right? It's from the last lecture. Okay, so briefly, I can, redefine what a candidate key is. Candidate key is the set of attributes of a relation that would uniquely identify the tuples from the relation. Okay, and you can have more than one candidate key. Okay, so a prime attribute type is an attribute type that is the part of a candidate key. So let's look at an example here. So in this example, you're looking at a relation R1, and that relation has the attribute types SSN, the attribute type P number, attribute type P name, and hours. Okay. Now here again, it's similar to the last example that we had in the previous slide, where an employee is working on projects. Okay. Now, yeah, an employee can work in multiple projects, and for one project, we can have multiple employees. And for that kind of scenario, our candidate key is going to have the social security number. I'm putting that as the first attribute, and the second attribute is P number. So in this case, our candidate key is a composite candidate key. We can have an atomic candidate key as well. Okay. Now, when you know that your candidate key has two attributes, right? Social security number, SSN, as well as P number, then SSN and P number, if you take them, one at a time, then these are what? These are the prime attribute types. Okay, so here the prime attribute types are SSN and P number. All right, so you might be thinking like, what will happen if I have only, if my primary key is single attribute type? Then I'll say, okay, that single attribute type is your prime attribute. Okay, good, fine. So once we have identified SSN and P number as the prime attribute, then whatever we are left with in this relation, like P name and hours, these are going to be non-prime attributes. Non-prime attribute types here are P name and hours. Guys, this is important too. I would say the whole lecture is extremely important. What next? Now we will get into the normal forms in more systematic way, and we will discuss 4 normal forms. The very first normal form that we will learn about is going to be first normal form. That will be followed by second normal form, then the third normal form. We will then discuss, BCNF, that's boys called normal form, and finally we will discuss the fourth normal form. So let's start with the first normal form. So the first normal form, which is also referred to as 1NF, it states that every attribute type of a relation must be atomic and single valued. Atomic means it cannot be further broken, right? Like social security number, SSN, is an example of an atomic attribute type. Okay, whereas an employee name is not an atomic attribute type, because the employee name can be further decomposed into first name, middle name, and the last name. Okay, and it should be single valued. As an example, social security number is a single valued attribute type, whereas the phone number is not a single value type, phone number and an email, because it is possible to have more than one value for the phone number as well as email. So here we have it now. We should not have no composite or multi-valued attribute types are allowed. And in fact, this property of first normal form, which says that every attribute type of a relation must be atomic and single valued, is the same as the domain constraint that we learned in the last lecture. Okay, so you should know this mapping, like the domain constraint is equivalent to first normal form. which says that all the attribute types of a relation should be atomic and should be single valued. And in domain constraint we have one more constraint, that these values that we are having for these attributes for a relation, they should get the value from their domain type, right? So that domain thing is also to be added. So let's look at an example and try to see whether this example of the relation is in first normal form or not. So here again we are looking at the supplier relation, and the supplier relation has the attribute type supplier number and R, and then the name of the supplier. For name we are using this notation because it is composite. Name has the first name and the last name and the supplier status. Okay, so is it in the first normal form? No. Why? Because of the second attribute type that we have, which is composite here, right? So the culprit is over here, the name. Name attribute type of supplier is the reason why the supplier relation is not in first normal form. So how to make it first normal form? Fairly simple. And here we go. Right, this is the solution, and I'll explain to you why is this in first normal form. Well, for supplier, right, we have normalized, right? This was not in first normal form. How do we normalize it? How did we make it to first normal form? Well, we did not have any problem with supplier number, SUPNR. It is atomic, it is single valued. But name was composite, right? So we broke that down into the first name and the last name. Right now, the first name is atomic. First name is, single value. The last name is atomic single value, and supplier status. With supplier status we did not have any problem at the first place. Okay, so yeah, interesting example, right? Now we have another very interesting example of the first normal form, right, where we would see whether the given relation is in first normal form or not. If not, then how can we change that to first normal form? So the example of the relation that you're looking at here is department. It's a department relation. And for department relation, we have the attribute types department number, department location, and department manager SSN, right? So D number is the attribute type for department number. D location is the attribute type for department's location. And DMGR SSN is for the social security number of the person who is serving as the manager of the department. Good? Fine. So let's look at the assumption that we have here. The assumption is that a department can have multiple locations. Okay? And multiple departments are possible at a given location, right? So let's think about it. Okay, I will use Stony Brook as the example of location. So let's think of Stony Brook as a bigger city where we have a lot of industries there, right? So it's possible that we may have not industries. I think it's fine to just think about departments, right? And for departments, I'll say okay, computer science department, electrical engineering department, just making it entirely very simple very simple to understand. Then in Stony Brook, we can have multiple departments, right? Like computer science department, electrical engineering department, material science department, humanities department. So one location can be shared by multiple departments, and that is very practical. And one department can have multiple locations. So like the computer science department can have one location in Stony Brook University, in Stony Brook, and the computer science department can have another location in Manhattan, right? So this is possible, right? So yeah, that's our assumption. A department can have multiple locations, and multiple departments are possible at a given location. So although this relation looks very simple, but yeah, we need to keep this thing also, right? This assumption as well. So if you follow this assumption, then what will happen is, then you realize that this thing that we have, let me put a rectangle around this attribute type, which is delocation, then this is multi-valued. Okay, one department may have multiple locations, right? And first normal form does not allow multi-valued attribute types. Okay, because in that case, if you're allowing to have multiple locations for a department, then yeah, in this single cell you'll have multiple values, which is against the rule of first normal form. So here we go. How do we normalize this department table so that it is in first normal form? We'll have to break this table down into department number and the manager, right? D number and the MGR SSN. Okay, because for one department we have only one manager. Okay, so yeah, department number is atomic, department manager SSN is atomic, right? And they are single value too. So this is in first normal form. Good. Now, we need to take care of the department location as well. So what we would do, we would have another relation, simpler one, where we would keep the department number and the D location. Okay, and if you think about this new relation that we created, which we are calling as DP location, then here these two attribute types that we have, the only two attribute types that we have in this new relation department location, they together form the primary key, right? So the primary key of this new relation that we're calling as DP location is D number as well as D location. Okay, and pay attention to the fonts of D number. It is italicized. This is italicized. Why? Because you know what, D number, we are getting it from D number of the department relation, right? Therefore this prime attribute, this is a prime attribute for department location, right? Because that is the part of the candidate key or the primary key. This guy is the foreign key as well. The number attribute type that you have in DP location is a foreign key as well, right? So interesting. Guys, an important example. Good. So now what we will do, we'll look at an example to understand what we did. Okay, like how will this thing make more sense when we look at the data as well, when we look at the tuples as well. In our discussion till now, we were only looking at the relation. We did not pay attention to the state of the relation. Here in this picture, you're looking at the state of a relation. State of a relation is determined by the value that we have in those relations. Okay, so let me mark this as an A, YA. Well, that's the initial relation that we'll look at. And this relation, pay attention, has the attribute types D number, then D location, and DMG or SSN. Now D number is fine, right? Single valued, atomic. Look at location, D location. Here for this department number 15, there are two locations, New York and San Francisco. So this is what? Multi-valued. Okay, and same is the case for the department number 30. For that department also we have two locations, Chicago and Boston. All right, so yeah, the same thing, multi-valued. Okay, so in order to make sure that this relation stays in first normal form or should be in first normal form, we need to break it down as we have already seen. And once you break it down into two relations like department and the department location, DP location, then see, in department we will keep only the information about department number and the corresponding manager's SSN. So we have three departments here, 15, 20 and 30 as the department number, and then their managers SSN are 110, 150 and 100 respectively. Good. And in DP location we have the department number and the location, right? So for 15 we have two entries, one location New York, the other location San Francisco. For 20 there's only one location, which is Chicago. And for the department number 30 there are two locations, Chicago and Boston, right? So I hope the discussion that we had on first normal form is understandable. Okay, so well, we have one more example it seems. Let's look at the other example. Now the other example of the relation in as an example for a first normal form is R1, and this R1 relation has the attribute types SSN, ename, dnumber, dname, and project. So this project is an attribute type, okay? So don't get confused. It is an attribute type. And this attribute type is for the project information of an employee, right? We want to keep the information about the employee and the project that the employee is working on. Okay, and yeah, we need to make we need to be we need to remember the assumption. So I will read the assumption and then we'll come back to this example. We are assuming that an employee can work on multiple projects and multiple employees can work on the same project, right? So this assumption was there in our early example as well. Great. So yeah, for the project we are keeping project number, project name, and the hours. All right. So it's not in first normal form, right? Why? Because for one employee you will be probably keeping the project number for multiple projects that the employee is working on. Okay, and for one project number again you'll have to keep the information about different employees who are working, right? So it's not in first normal form. What we need to do is we need to make it to first normal form. How? Well, this way. In R11 we are keeping SSN attribute, then ename attribute. These two attributes are related with the employee entity type. And then for employee entity type, you would keep the D number. D number is the department in which this employee is working, right? And then the D name. D name is the name of the department in which an employee is working. Okay, that's one relation. How about the other relation? The other relation, which is R12 here, will have the attribute type social security number, SSN, P number, the project on which this employee is working, P name, name of the project, and hours, the number of hours the employee is working on that project. Okay, and here the R12 will have the two attribute types, SSN and P number. Why? Because there one employee is working in multiple projects and one project has multiple employees. Okay, and I think we have seen this example earlier as well, maybe in a different context. This SSN that you have in R12 is what? Is the foreign key, all right, as well as it is a prime attribute as well. Prime attribute. Why is SSN a prime attribute? Because for R12 the primary key has two attribute types, SSN as well as P number. Okay, so for R12 SSN as well as P number are the prime attributes, but only SSN is the foreign key here. And yeah, this has been this you can see from the way we have written SSN, italicized SNN. It's the slanted or the italicized notation. Fine, now let's move on to the next normal form, which is called second normal form or 2NF. For second normal form, we'll have to understand a kind of functional dependency. Okay, so please pay attention on that. A functional dependency, x to y, is a full functional dependency. Please make sure that you understand full functional dependency. A functional dependency from x to y is full functional dependency if removal of any attribute A from X means that the dependency does not hold anymore. What is A? A is an attribute that you want to take out from the left hand side of the functional dependency. What do we have on the left hand side? We have X. So whenever you have the functional dependency going from X to Y, and X is a set, right? And from that set, if you take one attribute out, say that attribute A out, and the functional dependency after removing A, if that does not hold, then we would say that this functional dependency is full functional dependency. So let's look at an example. So the social security number and P number would determine the hours, right? So for project, when the employees are working on multiple projects, then how would we find out the hours an employee is working on a project? We would need social security number as well as P number. because for one project we have multiple employees and one employee is also working on multiple projects. Therefore, the combination of social security number, which is SSN, and P number is required to determine the hours. Okay, so SSN P number is the candidate key or the primary key. We have the functional dependency SSN to P number. Now, if I either take SSN out, right, if I remove SSN and say, okay, find P number to hours whole, then that is incorrect. For this functional dependency, we need SSN as well as P number, right? So this is an example of full functional dependency, FFD you can write, right? Full functional dependency. Hours attribute type is fully functionally dependent on SSN as well as P number. Same is the case with the second functional dependency, which is from P number to P name. Okay, yeah. Now let's look at another kind of functional dependency, which goes over here. A functional dependency x to y is partial dependency. We have seen full functional dependency, right? Now let's think about the partial dependency. So a functional dependency x to y is partial dependency if an attribute A from x can be removed from x and the dependency still holds, right? So there are going to be some cases that will fall in the category of partial dependency. So let's look at some examples. So here we go, right? X to y. In x we have these two attributes which I am putting in the parentheses just to make sure that this is easy to follow. Guys, this is an extremely important concept. Okay, so I'm putting the stars over here. Social security number, P number, they are our x, and then in y we have only one attribute type, which is P name. In this functional dependency, if I remove social security number, that is going to be A, right? If I take this A out, then you know what? This P number, BER, P number to P name, right? It is still a valid functional dependency, right? Therefore, this is an example of partial dependency. Partial dependency when you can remove an attribute A from X and this functional dependency still holds, then that is partial functional dependency or partial dependency. Whereas in full functional dependency you can't do that. Okay, if you remove any attribute from X is on the left hand side, then functional dependency does not hold anymore. Good. So if we once we understood the definition of fully functional dependency, then yeah, we are prepared for second normal form. So what is a second normal form? A relation R is in second normal form or in 2NF if it satisfies first normal form and every non-prime attribute type A in R is fully functional dependent on any key of R, right? So this is slightly intense compared to the first normal form. Okay, I think the first normal form is probably the easiest one to understand. Second normal form is slightly harder than first normal form. Then third normal form is slightly even more complex than second normal form, BCNF, and fourth normal form, right? So that's the kind of progression that we have here. A relation R is in second normal form 2NF if it satisfies 1NF, and every non-prime attribute type A in R is fully functional dependent on any key of R, right? Now, if the relation is not in second normal form, then what we should do? Then we must decompose it and set up new relation for each partial key together with its dependent attribute type, right? So these concepts will make more sense once we work on an example. Now, what is decomposition? Decomposition is something we'll have to do on a relation which does not satisfy second normal form. We'll have to decompose it and set up a new relation for each partial key together with its dependent attribute type, and we would also keep a relation with the original primary key and any attribute types that are fully functionally dependent on it, right? We need example badly to understand this concept. Here we go, right? So here is our example. to understand the second normal form. The relation is R1 and the attribute types are SSN, P number, P name and hours. Good. So let's read the assumption first and then we'll start working on this relation. Assume that an employee can work on multiple projects and multiple employees can work on the same project and a project has a unique name. Good, simple enough, right? We were already using this assumption in some previous examples. Good. So here we need to find out what is going to be our primary key. All right, so our primary key would be the combination of social security number as well as P number. Right? Why? Because an employee can work in multiple project and one project will have multiple employees. So just one attribute is not going to work here. We will need two attribute types and these are SSN as well as P number. Now with these two as the attribute types, right? These two attribute types as the primary key, we'll have to think about different functional dependencies. All right. So the first functional dependency, which is simpler to understand or find out, is going to be SSN, P number. This is our X, right? To Y, Y is going to be hours. Okay, so for the hours, uniquely find out the number of hours. You need the combination of SSN and P number. Right, on the left hand side, X is our primary key and hours here is fully functionally dependent on SSN as well as P number. We need both. Whereas if I take another example of the functional dependencies, which is SSN, P number to P name, right? Then here P name is in fact only dependent on P number, right? So P name is partially dependent on SSN P number, okay? And we don't want this kind of functional dependency. If we keep that, then that is not in accordance to second normal form, right? So we have to break this table. And here we go. How do we break? Well, we will keep these three attribute types together, right? Like R11 with SSN, P number and hours. Why? Because they are perfect, right? We have one functional dependency, which I have, listed over here, and we are fine with that. That here, the hours is fully functionally dependent on our key, right? Good. That is in accordance with second normal form. Right, and what should we do with the P name? Well, for P name we have an interesting solution. We would create another relation R12 where P number is going to be the primary key and we'll put P name. Right, now once you created R12 a new relation which is in second normal form now, then this second attribute that you had in R1 will be a foreign key. Why foreign key? Because we will be able to connect these two relations together by using this P number, and which is being used as the primary key in the second relation. Okay, so you need to understand these concepts and you should be ready to work on some kind of these kind of problems for the normalization. If somebody is giving you a relation is asking whether a relation is in a particular normal form or not, so you should first be able to evaluate whether the relation is in, say, second normal form or not, and if not, then you will have to decompose it to make it into second normal form. And for that you need to have the understanding of the full functional dependency and partial dependency. Partial dependency means you need to decompose the table. Any partial dependency in the relation. Good. So what we will do now, let's look at an example of the relation state. The previous relation that you saw, for that we are thinking about the tuples now. So for a relation, right, over here, I'll call that A. We have the data, SSN, P number, P name, and hours. Good. Yeah. So now just look at this data and see if this data looks good or not. Right. So what I would say, you need to look for redundancy, and here we have the redundancy. 1000 is the p 1000 is the p number, and the p name is Hadoop. 1000 again, p number, name. 1000 again, 1000 for p number would correspond to the same project name. So we have a lot of redundancies here. Okay, so which is bad. We'll have the inconsistencies, and we will have the storage wastage, which we want to optimize, we want to reduce using normalization. Now the very moment you broke this table down into, or this relation down into the relation B and C, now look at it. In B, you're keeping p number and name. Good. And in the other relation that we have, which I'm calling as C, you're keeping SSN, p number, and hours, right? And look at it now. We don't have much of redundancies, right? So here you would say, okay, fine, this is repeated. P number 1000 is repeated 3 times. So that is repeated 3 times because we have 3 employees. One with SSN 100, the other one with SSN 280, and the third guy with the SSN 120. So this repetition we cannot avoid because there are 3 employees working on that project. Okay. Now, one more advantage that we have with this kind of normalized situation is that if for some reason you later on decided to change the name from Hadoop to big data, right, then that is not a problem. You need just one modification in the project table. Okay, so this could be called project, because here we have the information about project, only project number and p name, and this should be works on, right, because you have the employees information which is coming in SSN, and then the project number and the hours that an employee is putting on a specific project. Okay, important. Fine, now what we will do, we'll learn about the third normal form. So for that also we would have to understand another functional dependency. So let's get that thing done. A functional dependency x to y in a relation R is transitive dependency if there is a set of attribute type Z that is neither a candidate key nor a subset of any key of R, and both functional dependencies x to z and z to y hold. Okay, one more time, important, one more time, let's try to understand what we are saying here. A functional dependency x to y, here again we are not saying anything about third normal form. We are making sure that we understand an interesting kind of functional dependency which is related with third normal form. This is the transitive functional dependency or transitive dependency. A functional dependency x to y in a relation R is a transitive dependency if there is a set of attribute type Z that is neither a candidate key nor a subset of any key of R, and both x to z and z to y hold, right? So it's a kind of transitive thing which is happening. You have x to z and z to y, then that means x to y. Okay, so that transitive dependency should not exist in third normal form. Okay, so that information we have here, which defines our third normal form. So a relation is in third normal form 3NF if it satisfies 2NF and no non-prime attribute type R is transitively dependent on primary key. Okay, so this is something that I should have explained to you earlier, but I think I forgot to do that. Sometimes in the text you would find this kind of picture: one rectangle, another rectangle, smaller one, then a smaller one, so on and so forth. I don't have much space, so I can't write much. So 1NF, then inside you'll put 2NF, then you'll put 3NF. The message behind these kind of pictures is that a relation would be in 2NF only when that relation is already in first normal form. Okay, for second normal form, it is required that the table should already be in first normal form. Then you will think about the full functional dependency and all. And similarly, for third normal form, your relation should be already in second normal form. If the relation is not in second normal form, it can't be in third normal form, right? So the same thing applies for the higher normal forms. Okay, so a relation is in third normal form or 3NF if it satisfies 2NF and no non-prime attribute type of R is transitively dependent on primary key. For this also we will need an example. Now before we go to example, let's see what we will do if a relation is not in third normal form. If the relation is not in third normal form, we need to decompose the relation R and set up relation that includes the non-key attribute types that functionally determines the other non-key attribute types, right? So what we are saying here is we need to take care of this thing, Z to Y kind of relationship, right? Because what is Z? Z is a non-key attribute type, right? And Z is is an attribute type which is coming in between and messing it up, right? From X to Y, X is probably a prime key, X is a candidate key, but yeah, we have a Z in between, and there is a functional dependence from X to Z and Z to Y. Okay, yeah. So if you find something like this, then yeah, we have to take care of that. Let's look at an example. Here you have the relation R1 with the attribute types SSN, ename, dnumber, dname, dmgr, ssn. Okay, so I'm not discussing these things because probably I already discussed it. You should be prepared to evaluate whether this R1 is in first normal form or not, whether it is second normal form or not, whether it is in third normal form or not, that we have to discuss right now. But yes, do it as a homework. See whether it is in second normal form or not. Okay, whether it is in first normal form or not. But anyway, for this R1, we are making some assumption. What are the assumptions? Assume an employee works in one department. A department can have multiple employees and a department has one manager. Good. All right. So here we have social security number SSN, e-name, D number, D name, and MG and DMGR SSN. DMGR SSN is the social security number of the manager of the department. Good. Fine. So what we will have to do, we'll see whether we have a transitive functional dependency or not. Okay. So you know what? Before I go over the examples that we have in the lecture notes, let me try to do it from the scratch, right? Using the pen. So our primary key is SSN, which has been underlined here. Because if you know the SSN of an employee, you will tell the name of the employee, you will tell the department number in which that employee is working, you can tell the department name as well of the employee, and you would also tell the manager of that employee's department, right? Yeah. So what we have here, we have this functional dependency from SSN to social security number to DNAME. Right? If I know the social security number of an employee, I will tell the name of the department where the employee works. So we have this X to Y functional dependency. But you know what? There's this interesting attribute type D number over here, which is Z. Why is that working as a Z? Because if you give me Z, right, I'll tell Y. What is Z? D number. If you give me D number, then I'll tell you the department name. Right? But what? This Z, I also have X to Z. Right? What is X to Z? Social security number to D number and D number to D manager. So D name, right? So in fact, we do have the transitive functional dependency here. And because of the transitive functional dependency, this is not in third normal form. We need to fix it. So how do we fix? We'll have to break this thing down. What do we need to break? This Z to Y is causing a problem, right? So we will take D number, and D name out of this table. Okay, because here only we have the problem, right? And then, yeah. So in that effort, what we did, we'll break R1 into R11, and in R11 you will keep the SSN of the employee, the name of the employee, and the number of the department where the employee is working. Good. And in the second table, which we are calling as R12, you'll keep the D number, right? D name, D number is working as our Z to Z to Y you'll keep, and the manager's SSN, department manager's SSN, right? And in this decomposition, what will happen, the social security number SSN will be the primary key of the first relation R11, and D number will become the primary key of the second relation R12. And since you need to combine these two, you'll have to join, right? We'll learn about join and all later. So we would have to keep this D number. Well, anyway, we will need the D number for an employee, right? Because we should know which department this employee is working. And this D number here is becoming a foreign key. And this manager DMG or SSN will now serve as a foreign key because it will get the value of SSN from the R11. Okay. It's an extremely important concept and an extremely interesting and useful example as well, right? Which will help you understanding the third normal form. And as we always do, now we'll look at the example tuples and see how the life is changing after making after decomposing the non-3NF relation into 3NF relation. So here we have the SSN, then the name, D number, and D name, and manager SSN. Okay, so our interest is in looking at the redundancy. For that, I will put a rectangle here, one more rectangle here, and then the third rectangle here. And by putting these rectangles, I just want to highlight the redundancies, right? See, 1, 2, 3. We repeated this information at 3 places. So, whenever you will have the department number 10, you will have the repetition for department name and the department manager's SSN. Okay, so how should we fix it? Well, let's break it down. Okay, so if I call it A, this becomes our B, and then C. In B, we are keeping SSN, name, and D number, right? And for the third relation, we'll keep the department number, department name, and manager SSN, right? Now look at it. We don't have the redundancies anymore. I mean, the kind of redundancies that we had in A is being reduced. Okay, that's an interesting example. What we'll do next, we will now look at BCNF, Boyce Codd normal form, an extremely, probably the most important normal form. Okay, the most important normal form, I think, is BCNF, Boyce Codd normal form. So for that, we'll have to, look at the functional dependency again. So a functional dependency from X to Y is called trivial functional dependency if Y is a subset of X. Right? So this, the concept of trivial functional dependency could be important as well. And initially you will find it confusing, like, yeah, it's not making sense, right? But yeah, theoretically it makes sense, okay? So make sure that you understand the definition of trivial functional dependency. Because the BCNF has non-trivial functional dependency in its definition. So one more time. A functional dependency from X to Y is called a trivial functional dependency when Y is a subset of X. So as an example, look at it. X over here is SSN and name. This is your X. And Y is just SSN. So Y is in fact the subset of X. X has two attribute types, SSN as well as name, whereas Y is just SSN. So here, clearly Y is a subset of X. Yeah, I'm using the subset in notation. Good? Fine. Now, to the BCNF. A relation R is in BCNF, is in Boyce Codd normal form, provided each of its non-trivial functional dependency, right? It should not be the trivial one, not like this. We in BCNF, the functional dependencies should be non-trivial functional dependency. So a relation R is in Boy's chord normal form provided each of its non-trivial functional dependencies x to y, x is a super key. Super key we discussed in the last class, right? So what does it mean? It means that X is either a candidate key or a superset of candidate key. All right, so that is the restriction. BCNF says that for its all non-trivial functional dependencies, for each non-trivial functional dependencies of the form X to Y, X should be a super key. Now, one interesting thing about BCNF is that it is stricter than the third normal form. It is also called sometimes 3.5 normal form. 3.5 enough means the BCNF slightly, strict compared to third normal form. So if your relation satisfies BCNF, then that means it will by default satisfy the third normal form as well. Now, what we have here, every relation in BCNF is also third normal form, not vice versa, right? I just went over that thing. We will use an example to understand this BCNF and how can we make a relation to BCNF if that is not already in BCNF. Okay, so in the example, we have relation R1. R1 has the attribute type sup and R, sup name, prod and R, and quantity. Sup and R is supplier number, sup name is supplier name, PROD and R is product number, quantity is quantity of the product. Okay, so here the assumption is that a supplier can supply multiple products and a product can be supplied by multiple supplier, and supplier has a unique name. Good. Now, if you're given this information about R1 and this assumption, then from that assumption you will have to come up with the primary key, okay, or the candidate key or a super key. So since we have this assumption that a supplier can supply multiple product and a product can come from multiple supplier, therefore our primary key is going to be supplier number as well as the product number together. All right. Yeah, so once we understand that, then we will look at the functional dependencies. Okay, so before we look at the examples, this hint is enough. Once you identify the candidate key or a primary key, which is supplier number as well as product number, then you know what, this kind of functional dependency which we have here, which is sup and R, supplier number to supplier name. Right here, our left hand side, which is supplier number, it is not a candidate key. It is not candidate key. Sorry, here we are using super key thing, right? It's not a super key. Therefore, it's not in BCNF. All right, so this is what you have to think about. Anyway, so how will we make it as a BCNF? We'll have to break it down. And by breaking it down, you will have one relation R11 where you will keep the supplier number, the product number and quantity. Okay, and in the second relation you will have the supplier number and supplier name. Good, right? So here for the first relation R11, which I marked as 1, there's no problem, right? Because the functional dependency here is supplier number, product number to quantity, right? So here on the left hand side, X is a super key. And for second relation also, our functional dependency is from supplier number to supplier name. Again, supplier number is a super key for R12, right? So yes, now the relation R11 as well as R12 are in BCNF. R1 is not in BCNF. Okay, guys, make sure that you're following these things. Do these things as an exercise, right? And convince yourself. It's the same thing. Sorry about that. I have duplicate slides here. Fine. So the last normal form that we will discuss is the fourth normal form. And for fourth normal form, which is important as well, we'll have to understand another kind of functional dependency. So let's discuss that. It is called multi-valued dependency. So there is a multi-valued dependency from X to Y. What is X and Y? X and Y are again the attribute types from a relation R, right? And here we want to understand the multi-valued dependency. So there is a multi-valued dependency from X to Y, for which we will now use the symbol two arrows, X to Y, right? Two arrows. For the normal functional dependencies, we had just one single arrow, X to Y. In multi-valued functional dependency, we will use double arrows, right? So there is a multi-valued dependency from X to Y, which we will write as X double arrow Y if and only if each X value exactly determines the set of Y values, multi-valued. If you know X, then you'll know the multiple values or the set of values that would be implied by X, right? I should not have used the word imply, because imply has, other mathematical notions. But anyway, there is a multi-value dependency from X to Y written as X double arrow Y if and only if each X value exactly determines the set of Y values independently of any other attribute types, right? And yeah, I know that this is a little tricky, but once you know the exam, we go over the example, then yeah, it will make a lot of sense. So now, if you followed the definition, then we can think about the fourth normal form. A relation is in fourth normal form for NF if it is in BCNF, voice code normal form, and for every one of its non-trivial multi-value dependencies, X to Y, X is a super key. That is, X is either a candidate key or a superset thereof. Okay, so let's work at an example. So the example that we are using to understand the fourth normal form is over here. R1 is the name of the relation, and the attribute types are course, instructor, and textbook. Now let's look at the assumption. Assumptions are that a course can be taught by different instructors, and a course uses the same set of textbook for each instructor, right? So the hint over here is, let me read this one more time. A course can be taught by different instructors. How many, we don't know, right? But maybe more than one or just one. So a course can be taught by different instructors, and interesting thing is a course uses the same set of textbooks for each instructor, right? So what we have here is course to multi-value dependency to textbook. All right, so as an example, if the course is database management, then probably we can think of 3 textbooks for that course, right? Doesn't matter whoever the instructor is. If the course is database management, then yeah, these are the 3 textbooks. Okay, so the course determines the set of textbook irrespective of the instructor. Doesn't matter who's the instructor. If this is the course, then yeah, these are the 3 textbooks that we will have to use. Okay, so here we have an example of multi-valued functional dependency. And the course to textbook is multi-valued dependencies independent of instructor. Good. And fourth normal form says that if you have a non-trivial functional dependency like this, then what you have on the left hand side, which is course, it should be a super key. Is that the case here? Is course the super key here? No. Right? Because no, course is not super key here, right? Because the same course has multiple textbooks and the same course has multiple instructors. So, you should expect multiple records for the course number. Okay, so it needs to be broken down into 2 relations. So how will you break that? In R11, you will keep the course with the textbook and look at it, course along with the textbook, they are both taken as the primary key. And the second table would be, or the second relation would be course and the instructor. Here also, we would need both the attributes for the primary key. Let's look at an example for fourth normal form. The course is database management, right? So in all the 4 tuples, 1, 2, 3, 4, this is the original relation, or the table I should call it, because we have all the tuples. This is not in fourth normal form, right? A that you have here is not in fourth normal form. B and C is what we get after we decompose A. So the database management has these two books, the database cookbook and database for dummies, right? So these are the two textbooks that we have for database. And the instructors are two instructors, right? So instructor 1 and instructor 2. So that's the original uh, table that we have. We need to break it down in accordance to the relations that you saw in the previous slide. So what will happen next? Well, in B, if you look at, you have the course and the instructor. So database management taught by two instructors. The course has two textbooks, right? Database cookbook and database for dummies. Now, in this kind of scenario where we have normalized our table to the fourth normal form, now our life is a lot easier. Why? Because you know what? You can add one more instructor here by doing only one entry, right? Let's have a new instructor, like I'm putting myself there. So there will be only one entry here. Otherwise, if we had to do that here, then you know what? You'll have to make two entries for me as an instructor, because I need to be associated with these two textbooks that we have. Okay, so yeah, the fourth normal form is even better, and fourth normal form makes sense when we have multi-valued dependencies. Okay, so let me stop right here. I will see you in the next class. Bye bye. Thank you. Take care.